This meeting is being recorded.
Okay, so for this session, we are going to discuss about the microwind software. Okay, so probably this software we will be using to conduct the practical, and I will introduce you, or I will make you familiar with this software. And it's a kind of simulation tool that is available to execute and to design different Boolean equations, different logic gates, universal gates, right? Using CMOS. Okay, just wait for a minute. Okay, let me share the screen. Okay, screen is visible. Screen is visible.
Yes, sir.
Okay. So see, this is a software microwind version 3.1. Okay. So what are different tools? What are different options that are available in this software that I will explain so that you can familiar with this tool. So basically, this software is or this tool is used for to design different logic gates or any kind of you can implement boolean equation using CMOS. Okay, so now you are all are familiar with the what is CMOS, right? It's a combination of PMOS and NMOS, right? So whenever you have to design particular logic gate or anything, any digital circuit using CMOS, you can use this software, right? So this entire portion, this black portion, so you can treat it as a p well. Okay, you can treat this entire black portion as a p well. That means what? See, in a case of CMOS, there is a PMOS and NMOS, right? So PMOS, what is or how we are actually uh, constructing the PMOS? So you have a n n diffusion region, or you can say n well. Then you have a p substrate on that, right? Then you have a polysilicon, right? So in second chapter we have studied the different circuit design rules for the CMOS. So by using that circuit design rules, you can design different logic circuits. Okay, using this microwind software. So in that case, this entire black portion will be the PMOS. Okay, sorry, P well. Then you have to uh, look for this option. So you can see the gun symbol here. So basically this option is used for the delete purpose. So you can see here it's showing that you if you want to delete a particular object, so you can delete something from the layout. So this next option is the copy element, right? So you have designed one inverter circuit and you require such a more number of inverter circuits. So what you can do, so you can simply copy that inverter and you can paste it. Okay, or you can make a copy of that as much as you want. Okay, then this is a stretch option. So what is use of this stretch option? So if you want to move a particular layout or particular PMOS or NMOS from one place to other place, so you can select that and you can move from here to there. So it's a kind of just to move that particular object from one place to another place. This is a zoom in, this is a zoom out, and this is a view all. That means if you click the option, it will fit within the your what we can say the view area. That entire design it will fit within a view area and it will show you in that aspect. Okay, this option is used to run the simulation. Okay, this option will actually measure the distance, because see, whenever we are designing a CMOS or PMOS, you have to obey or you have to follow some design rules, right? For example, the minimum length is a 4 lambda. So basically this scale is used whether we are making our design, making our layout abide with the design rules or not. To check that, you can use this scale. Okay, so you can have the 2D vertical cross section view, you can have different 3D process steps. Okay, this is a design rule checker. Means what? Whatever the schematic or whatever the layout for any logic gate or any logic design you have implemented, whether that design is abiding with the design rules or not, or there is some error. So you have to check that with this design rule checker. This a symbol is to add some text. Okay, this a symbol is to add some text to your layout. This is a contact layer. This will show you the MOS characteristics, and this is nothing but this palette. Okay, if you close this palette, you can again reopen from this show palette panel. So it will show this palette. Here there are some options, metal 6, metal 5. So you can use this option to design your logic circuit. and this screen is nothing but, see, you can see the screen is moving upward, this screen is moving lower, this is from to left, this is to move to right. Okay, you can use this upward, downward, left, right key or left, right buttons to move the screen in that respective direction. Okay, so this is about this entire software. This is very easy to handle, easy to uh, use. Okay, it's a user friendly one. So now this is about the introduction to this software. Again, you will be more familiar when we will actual design something, okay, using this software. So now we will start with our the first experiment, design of CMOS inverter. Okay, now what is CMOS inverter? So you have a PMOS as a pull-up network, right, connected in series with the NMOS as a pull-down network, and towards the gate we are providing the input, and from the drain we are taking the output. Okay, that is a very simple construction of the CMOS inverter. So first we will try to design, it's a very simple circuit. So now how to start, with the design? So first you have to open this software. Second, go to the select foundry. Okay, when you choose this select foundry option, these many different micrometer technologies will appear in front of you. Normally we are choosing the CMOS 25 rule. Okay, that means the ratio or the ratio of that W by L is 25. So you have to click on the open. So now it will open with that 0.25 technology. Now you can see here is an option on this palette. This is a MOS generator, this is a complex contract, this is a virtual capacitance, this is a virtual resistance, this is a virtual inductance. Okay, now how to proceed with? So first you have to choose a MOS generator. Now first we will choose NMOS. Now here you have two options. Okay, you can choose this length and width in case of microns, or you can choose in case of lambda also. Okay, so minimum width is 4 lambda, that is the standard. So we can choose here a 4 lambda here. Okay, the number of this MOS is a 1, because we will require only one MOSFET. If you want two or more MOSFET, so simply you can click here 3. Okay, it will generate a 3 n type MOSFET. If you click 5, it will generate a 5 type MOSFET. So here in case we will require only one, so we will choose only one. Now here you have to generate device, you have to click on the this black background, and it will get a NMOS generated. Now this is a NMOS. Okay, now what are terminals of NMOS? This is a drain, this is a gate, this red is a gate, and this is a source. Now here is one interesting thing. In case of this particular software, you can make any one terminal as a gate, sorry, drain and source. That means I can consider this one, the left side one, as a source and right side one as a drain, or I can consider this left side one as a drain and right one as a source. It's a interchangeable, and the middle one is always a gate. Okay, this red part is always a gate. So this middle part is the gate. Okay, now this is about a NMOS. Now similarly you have to generate a PMOS. Now again go to this MOS generator option. Now click on PMOS. Okay, now you can choose this PMOS with the same lambda. You have to click on generate device, you have to click here. Now this is your PMOS. Okay, now by using this stretch option you can select this, and now you can adjust this exactly. You have to make very align with the uh, this NMOS. Now whether this distance is sufficient, you can get to know from this design rule. Okay, you have to click on this design rule. If there is no error, it will not show anything, but if there is error, it can show you the error. Okay, the distance between the metal and the polysilicon is less than 3 lambda, that kind of errors that will show. For example, see, I will put it very closer to this. Now see what error it will show. Now if you will see here, now see, it is showing that the spacing between the metal is less than 4 lambda. That means what, you have closed this very close to the NMOS. Okay, now what you have to do, you have to again select this and you have to move away from this. Okay, now see, and again if you check now, it will not show any error. Likewise you have to proceed with. Now we have chosen the PMOS, we have chosen NMOS. Now we have to design a CMOS. Okay. Now how to design? Now you can choose, as I told you, you can treat this terminal as a source or this terminal as a drain, or you can exchange. Okay, it's up to you. But this red one will be always a gate terminal. Remember, you cannot exchange this. This red part, this polysilicon is always a gate. This left side part, you can treat it as a source or drain, or vice versa. Okay, similar is case with this NMOS also. This red part, this red polysilicon is a gate. The left side part you can treat as a source or drain, or vice versa. Okay, now all of you are aware with the CMOS circuit. Okay, so the source of PMOS is connected to VDD. Okay, so now we will assume that this left side part is a uh, source terminal. So we will just extend this metal. Okay, and now from this, see, here is a VDD supply, so we will choose this VDD supply and we will connect here. Now this is our source terminal, and remember this, the background is a P well, but in case of PMOS you can see there is a N well, right? The PMOS always comes with the anvil, because in case of PMOS there is no ready-made anvil is available, but in case of NMOS this background itself is a P well, so that's why there is a no P well separately given in the layout. Okay, so you have to apply this VDD in this anvil also. I have applied to anvil. Always remember, in case of PMOS you have to apply source separately, and you have to apply the VDD to that anvil also. This green box, whatever the within this green box, it's a anvil. Okay, and this background itself is a P well. So in case of NMOS there is a no separate requirement of P well. This background itself is a P well. Okay, so we have did this connection. Now we have to connect the gate of PMOS and NMOS together. So we will choose the polysilicon and we will connect the gate of this both very carefully. Okay, done. Now these are the gate. Now to this gate, okay, we can extend this polysilicon little bit over here also. Okay, this. Now to the gate, we have to apply input. Okay, so where to choose input? So here is a clock generator, add a clock. So you have to click here and you have to place this clock here. It will show the output. So we will give the name as a input. You can change the name. We will make it little bit slower, and if you click assign, it will show, it will get assigned. Now see, here is a clock input we have applied. Now this is a source, this is a drain. So let me extend this drain to the drain of NMOS so that we can take the output from this NMOS like this. Okay, and now in this case, in case of NMOS, this is a drain and this will be the source. Now what to attach with this source? So ground supply. So here I will choose ground. I will connect here. It is a ground. And now this is the output. Okay, the drain we have shorted, the gate we have shorted, and we have applied the input, and to from this drain we are taking the output. Now how to check the output? So here the I symbol is there, so visible node. So you have to select this, you have to connect to this. Now it will ask you to level, you can keep it as it is, or you can change its name. I will change to output and assign. Okay, now this is the PMOS. This is the source of PMOS. I have connected with VDD. This is the drain of PMOS. This is the drain of NMOS. So we have sorted that. We have taken the output from that. And this is a source of NMOS. So we have connected that to the ground. Okay, and from the this gate, okay, we have made this gate terminal of PMOS and NMOS common. That means we have shorted that and we have applied the input. Okay, now before we will run the simulation, you have to check the design rules. So I have clicked on this design rule checker. Nothing is showing. That means what? The design is perfect. We have followed every design rule. So there is a no error. Okay. Now you have to run the simulation. How to run this simulation? You have to click on this run simulation. So it will get into this simulation window. Okay. Now this is the input, this is a output, as this is a inverter, right? As this is a inverter. So how you can check this? So for zero input there should be one output because it's an inverter, right? When there is a zero input there is a one output, and for when there is a one input there is a zero output. That means what? The circuit behaves very properly. And now if you want to check the frequency, okay, you can select here options and you have to put on a reset. Now it will show the frequency also. Okay, and this curve also for 0 1 1 0, again for 0 there is 1, for 1 there is a 0. Okay, in this way you can actually get the output. If you want to check the fast Fourier transform of this, you can click here. It will show the FFT of this clock signal. Okay, so this is a FFT, fast Fourier transform also. You can check here. Now, whatever the VI characteristics of CMOS inverter, that VTC, so choose here voltage to voltage curve, and now see, you can see here. This is a VI characteristic, the same characteristics we have discussed, right? So here is a region 1, here is a region 2, here is a region 3, here is a region 4, and lastly region 5, the 5 region working operation. And this is actually this midpoint, right? Where the both NMOSes are short for a very short time. And this is a your switching threshold, right? This middle point to the exactly half of the graph is a your switching threshold. That means what? At this point the power dissipation is maximum and the both CMOS and PMOS are in on or are in conduction. Okay, so you can check this type also. Again we will switch back to a voltage versus time. So you can check voltage versus current also. You can check voltage to voltage characteristics. This is also showing. Now frequency versus time. This is also frequency versus time, and this is a kind of eye diagram. Okay, so this is a eye diagram for CMOS inverter, and this is our for 0 1 1 0 0 1 1 0. That means whatever the circuit we have designed, it is accurately working. Getting the things? समझता है का how to use this software? So if you close this simulation window, it will get back to our design. Okay, okay, now the second practical that we will go for is the common source amplifier. Okay, now how to design the common source NMOS uh, amplifier. So first, what do you mean by common source? Common source means what? How to design common source? Let me show you the common source. Okay. See, this is what the common source. Okay. These are the source terminals made common. Okay. The source terminal made common, and the we have applied input to the gate of this NMOS, and this again gate is connected to the either VDD, or you can connect with the output also. Okay, this is a common source, and this is drain, and this is drain. You have sorted with the this particular uh, output. So this is a common source amplifier. Okay, now we will try to design this with the help of this simulation tool. Okay, so again I will switch to our design. Now what changes that I should do? So first let me modify something here. I will remove this. Okay, I will remove this output. I will remove this. Okay, VDD, this VDD, this VDD. Okay, now again I have the separate NMOS, or uh, let me do one thing. Again we will take the NMOS and PMOS. So I will check. Okay, now I have deleted everything. Now again show palette. First what we have to do, we have to do first choose PMOS and NMOS. So first NMOS. Okay, it's a lambda and we will require only one NMOS. So generate device, put here. This is a PMOS. So shift here little bit. Okay, now NMOS this with the same lambda, generate device, put here. This is your, okay, this is your PMOS. Now what to do? First we have to connect the drain. Now in this case we will assume this as a drain. Okay, we will assume this as a drain. So choose metal one, extend this part little outside this. Okay, so this is drain. For drain we have to apply this VDD. I have applied the VDD, and also within this N well also we have to apply VDD. Now where we have to take the output from the source terminal. So now we will assume this as a source of PMOS and this as a source of NMOS. So we have to connect this. Okay, now this is a source of this NMOS, this is a source of PMOS, and we have to take the output from that. So we will assign this output node over here. We will give as a output assign. Okay, now see, we will apply here a kind of a sinusoidal waveform. Okay, sinusoidal waveform. So amplitude of say zero point 0.5, frequency will be 1000 hertz, and offset will be 1 point. Okay, this is no problem. This is we will take 1000 only, and amplitude zero point 0.5 volt. Okay, assign. This is output and it is a sine wave. Okay, now next where we have to applied input to the gate of NMOS, right? So let me select the polysilicon. this gate terminal I will extend over here, and I have to apply input to the gate of NMOS. So again I will show this clock I will put here, but now here I have to select this sinusoidal clock where amplitude 0.5, frequency of 1000 uh, 1000 megahertz, offset is 1.5. Okay, the remaining is same, assign. So this is now okay. I have to change the name also, so I will give here input assign. So this is the input to the gate of NMOS. Okay, now this is the source of sorry, drain of NMOS. So I will extend this here, and I have to connect this to the ground. This is a NMOS, and now only one connection is we have to made is we have to short this gate of PMOS, right? We have to short this gate of PMOS to the output. Now how to do this? You have to extend this up to here, and you have to connect this to the output. And now as we are connecting this polysilicon with this metal, so we have to choose this metal to poly contact, and you have to apply here so that this poly will get connected this metal. Okay, now this is what our common source CMOS amplifier. Check this design rule. Okay, now here is one error. The spacing between is less than 3 lambda. So what you can do here is again check this design rule. Okay, so you can reduce this. Now check, it is a 3 lambda. Okay, now you can do one thing. You can this you can move this. Okay, zoom out this, again cut this. You can move little bit away from the PMOS. Okay, now again you have to make some connections. Okay, now this okay, sorry, control U you can always use. Okay. Yes, okay, so polysilicon I will now, sorry, yes, this part I have to choose here. Okay, fine. So input, again I have to apply here input. So I will choose here input. I will give input sinusoidal wave. I will check this parameters, assign. So here is now input. Now again check this design rules. So this extra poly surrounding contact is less than 2 lambda. Okay, so you can uh, make here some changes. Uh, now again check design rule. So this practical. Okay, so here is design rule. So this actually the metal surrounding this you can ignore because it will not affect your entire design that way. So this is our design. Okay, now you have to simulate this. Okay, what we have designed, the common source amplifier, common source CMOS amplifier. So after simulation, you should get the result. Okay, see, this is a common source amplifier. So as we have applied the sinusoidal input, so you can even check the frequency again, reset this. Okay, now here what I will do, I will make some changes. Instead of zero point 0.5, I will give 0.25. Okay, assign, and now we will simulate this again. Yes, now you can clearly see I have given only 0.25 volt of amplitude, and as a result you are getting the amplified output. Okay, and if you want to check the frequency, select this frequency option, reset here. You can able to see the frequency also. Now see, you can clearly check the frequency. Okay, you can change the scale, time scale, reset. See, within one there is an entire one cycle it will cover, and for this entire one cycle you will get as it is the amplified version. Okay, without phase shift, because this is a common source amplifier, we have not made an inverter, right? So you can check the FFT here also, fast Fourier transform. So as it's a sine waves, there are no the side bands, right? It's a basic wave. So here is only a one frequency, and that to be a 1001 megahertz approximately. We have selected the same 1000 megahertz we have selected. And so if you take the Fourier transform of this, you will get only a first ringtone, no side ringtones. Okay, for a square wave, definitely you will get the side ringtones also. Okay, so in this way you can evaluate different. See, this is a voltage versus time. This is a voltage versus voltage curve. This is a VTC curve. See, you can see VC, the maximum voltage 1.25 volt at VDD by 2. Okay, at exactly this square. So voltage versus current graph also you can able to get here. This is a voltage versus current graph. Okay, this is a current. It is a 0.272 milliampere, and these are the, this green one is the input voltage and the red one is the output voltage that we have got, right? So different parameters also you can study. So this is our voltage versus time. See, don't panic if you're not getting the waveform. Simply click on this reset, you will get everything. Okay, it is showing the amplitude also. See, 1.5, and this is the amplitude of this. So in this way you can perform different logic circuit using this microwind software. Okay, so this is about today's session. So in next practical, we will try to cover the practical number 3 and 4, uh, design of Boolean expression and design of NAND gate. Okay, we will design one Boolean expression using the same CMOS logic circuit, and we also study the design of NAND gate. Okay, so you can save this as a, means if you want to save this, so you can save this here examples. Okay, so in this examples also you can save different many options. They have ready made also, they have given current mirror circuit and this DAC. Okay, then inverter, many circuits they have already given, so you can only simulate also. But if you want to design something new, you can do that also. Okay, here in the rules. Okay, so I will give as a CMOS common source. Okay, CMOS common source. And if you click save, it will get saved. And uh, whenever you want to open that, simply click here, open. So you have to choose that library where we have saved that, this MW31 folder. In that rules, in that this CMOS common source, if you click, it will get opened and directly you can now simulate this. Okay, so this is about the today's practical, this by using the microwind. So in next practical we will designing the basic gates like NAND gate, NOR gate, AND gate, OR gate. So basic gates and universal gates we will design using the CMOS logic. Okay, so this is about today's practical. We will stop here. If you have any query or doubt, you can ask me right now.